So we talked about the details of energy transfer, for how much energy you have to give something to make it go up a certain amount in temperature, or how much energy you have to give something in order to change its phase. But how does that energy actually get transferred? Well, there are three ways. The first one, so like energy transfer, the first one is conduction. So conduction is where you actually have molecules hitting other molecules and transferring that energy. Okay? And the only way it happens is for those atomic vibrations to hit another atom. So this mostly happens with regard to solids, or really, really dense things, where you have an atom that's vibrating and can come in contact with another atom that's nearby, and also give it some of its kinetic energy. So you have a transfer of kinetic energy between microscopic particles. Okay? So if you are stirring something in a pot of boiling water, say for example like you're cooking, okay, then the spoon that you're using will end up heating up as you're stirring, okay, because it's going to be receiving energy from the water that it's in. Okay, the water is going to be hitting that spoon, transferring that energy. Well, these spoon molecules are going to be vibrating in the structure that makes up the spoon, and therefore they're going to be communicating all of that energy up the length of the spoon, even to the part that's outside of the water. So the part that's outside of the water is still going to get hot because of all that transfer of energy, which means that your hand could get burned if you're using a metal spoon in a boiling pot of water. So I wouldn't recommend doing that. That's why usually there are plastic spoons or wooden spoons that people use to cook with as opposed to metal. So, but that's all about transferring of the kinetic energy between the molecules because they hit other parts and transfer that energy. Remember that temperature is a measure of speed, which also relates to the kinetic energy. So the more kinetic energy a particle has, the higher its temperature. So a greater transfer of kinetic energy means a greater transfer of temperature. Okay, a greater heat that's been transferred. Alright, so that's conduction. Another method is convection, and this would be bulk motions of a material. What do I mean by that? Well, when you have this pot of boiling water example again, you have the container that has the water, and you're heating it from the bottom. Okay, so the heat is impacting the bottom of your metal pot, and that bottom is in contact with the water. Okay, so you have a bit of a conduction process happening right there, where you have the hot metal surface that is then touching that bottom layer of water. So that bottom layer of water gets heated up. So what happens with a fluid like that, when it gets hotter, its density decreases, which means that it will start to rise, because that's what happens with a lower density in a material. The lower density will rise to the top because it will float. Okay? So you have that really hot water at the bottom and the colder water up here, and so that layer of water will rise up. Well, the colder water will then of course have to take its place, so that will sink down. And then also, this hotter water, as it moves up, will transfer the energy to the places around it. So that the other water that was there will end up also getting some of the energy from that. And so then, the other water at the bottom that's newly reached there will heat up and rise up, and the whole process will continue. Okay, until everything reaches like a roiling boil, you have all of this energy being transferred, and it's at some equilibrium point, potentially, for when it's actually going to be boiling. Okay, but it's because you have that hot material in the midst of the cold material that is then moving through the cold material and can give some energy off to the other cold material in these surroundings. Okay? It will do that because of the laws of thermodynamics. Since it's hotter and the regions around it are cooler, it's going to be giving that energy to that. Okay? So that's also what happens with the ground. That's how the air around us gets heated. The ground gets heated by the sun, and then you have the ground heating the air right above it, and you have the air then transferring that energy to the rest of the air around it. Okay. This convective flow also actually happens at the outer layers of the sun. You have energy from the inside in that gaseous plasma that then will come out and give us energy out to the surrounding area and radiate part of it away, and then drop down, and you'll have convective cycles and convective flows out on the outer surface of the sun. So speaking of radiation, that's the third way that you can transfer energy. And radiation is specifically photons taking energy from one place to another. So, light from the sun travels through space and gets absorbed by the ground. Okay, some of it will get absorbed in the atmosphere, but a lot of it will get absorbed by the ground. Okay, and so those photons will come in and impact, just like the sunbeam is doing to my hand right now, and those photons will end up being absorbed by the material. So that will happen right here. It'll happen with the ground, which will then be able to transfer energy to the air, like I mentioned just before. Okay, but those photons are directly produced by the sun. They leave the sun and they travel, and they give their energy off to whatever it is they actually end up impacting. Okay? But that's because of the direct travel of the photons, the direct transport of energy from one place to the next. It's really important to think of a photon as a little particle, or a little packet, end particle of energy, taking energy from one place to another place. Okay? So you can have all of those different types of energy transfers, whether they be because of the molecules that have energy, or because of direct energy deposit from or loss in the form of photons. Okay. Now, just thinking about what happens with this, for radiation, the amount of energy you get from the sun per second, there's 3.90 times 10 to the 26th joules of energy given off by the sun per second, which is quite a lot of energy. A light bulb, a 100-watt light bulb, will end up giving you 100 joules of energy per second. Okay, so the luminosity of this would be that situation, or the power that this is giving for the energy rate will be that number. So it all depends on what's going on with regard to what type of material you have that's giving off that energy. For stars and things like the sun, the power, or the luminosity, is related to, let me write it as power here, is equal to the Stefan Boltzmann constant sigma times the surface area, which for a star, for any spherical object, is 4 pi r squared, times its temperature to the 4th power. So, if you change the temperature, you're going to drastically change the amount of energy output because of this power of 4 right there. So, temperature ranges of stars go from like 3,000-ish Kelvin to like 50,000-ish Kelvin. And so the power outputs of those stars drastically changes. Okay, you have relatively low luminous red dwarf stars at those 3,000 Kelvin to really hot, really luminous O and B type stars at the other end of the spectrum for that 50,000 Kelvin temperature that they have. But anyway, these are the three ways to actually transfer energy, which will then be analyzed by the cues that I was mentioning with regard to changing the phase or with regard to changing the temperature.